So, Mr. Bergman, you've been doing all these new career explorations. I really haven't gotten to do that. So, I've decided I'm going to become
Mr. Sam?
a poet.
A poet?
Yes, a poet.
No way.
Yes, this chemistry is enough for me.
You don't think I should be all those things, a musician?
Oh, no, you found a few things that'll work for you, but I'd like to do a little exploring myself here. So, poetry. So,
poetry, really?
Most poets, they write about what they know, and I know about chemistry. So, I've got some chemistry poems I'd like to read for you.
Poetry with chemistry themes? I'm with that, yeah.
Okay, so this is my first one here. It's called Ode to Little Susie.
Ode to Little Susie.
Little Susie was a chemist. Little Susie is no more. For what she thought was H2O was really H2SO4.
Ah, I'm dying.
Because that was, sulfuric acid. All right, I have another one. This one's a limerick. I like limericks. Okay. Chlorine, chloride, chlorate. I can't keep all of you straight. You're out of my reach. Hypochlorite is bleach. Naming compounds is that which I hate. What do you think?
That was weak.
Weak?
Like a weak acid. Hypochloric acid would be a weak acid.
So I can be the poet and you can be a comedian.
Yeah, well, I was trying to keep up with you there.
Yeah, speaking of weak acids and bases, that's what we're going to be talking about here.
Should we talk about some weak acids and bases?
We should probably do that,
yeah.
Maybe
Okay.
do some more poems later.
Before we do that, as we do that, we need to learn that there are different ways to define acids and bases.
There are.
And so, actually, before we do that, we should talk about the properties of acids and bases, since that's our first slide.
Yeah.
Okay, hey, what do you know about acids?
Well, I know they're sour.
Oh, they taste sour.
Yeah, that's what they put in like this Laffy Taffy I'm about to eat here. There's probably some acid in it to make it sour.
Okay, and bases, you know what they taste? They taste like coffee because they're bitter.
They're bitter, yep.
Yeah.
Malic acid. That's what's in my Laffy Taffy to make it sour.
He's eating
malic acid.
Food and trying to talk at the same time.
Yeah, it doesn't work
Didn't your
very well.
mother tell you not to do that?
No, she didn't.
It's sour. What else do you know about acids?
Well, let's see. If I touch it, it's corrosive and it'll burn, eat through my hand. Not really burn, but give me a chemical burn. And bases are also corrosive.
Yeah, they're also, yeah.
Yeah. Sometimes even worse so on your body than acids.
In fact, the other thing about bases that you could also say, they're also slippery.
They are. If you touch them, they feel slippery. Now, I can't confirm this 100%, but I've been told at chemistry teacher seminars that it's because they're turning the oils in your fingers into soap, actually. It's called saponification, where it takes the fat in your finger and it breaks it down and turns it into a soap. Again, I don't know 100%, but that's what I've been told, so I still have to research that.
Yeah, those out in internet land, you'll have to correct us if we're wrong.
Yeah.
Okay, I don't know for sure. I had not heard that. That's pretty cool.
Yep.
What is the key chemical that makes acids acids?
Hydrogen ions.
H positive. Now, ladies and gentlemen, this is very important. It's not hydrogen. It's hydrogen ions. It must have this positive charge. Do not write H2. Do not write H. It is H with a positive charge. And then bases are hydroxide. You know, something that I should chat about real quickly here. I don't know if you understand this, but you have a tongue. Really? Surprise, surprise. That's a tongue. That's your tongue, and I'm sticking my tongue out and talking to you. All right, so that's the tongue. And back here in the back, this is what you can taste. What did you know, Mr. Sams? You're a biology guy.
Well, that's where the highest concentration of bitter receptors are.
Yeah.
You actually have them all over your tongue.
Yeah.
But the little map of your tongue is where you see where they typically are concentrated more.
Here on the outsides, you have the sour taste buds. Now, you're right. It's oversimplification to say that they're in one place. But here's the point. What is it the sour taste bud detecting?
Sour taste buds are detecting hydrogen ions. So when they're there, that's why it tastes sour. Because they go, oh, look, H pluses. There must be an acid present. I'm going to send a signal in the brain that says sour, sour.
You see, I have, just to give you a perspective to understand what this sort of means, at my house I have it's called a carbon monoxide detector.
Mm-hmm.
It is designed to protect my family in the case of carbon monoxide coming from my furnace and, gassing us to death. And so all day long it's sniffing, if you will, or trying to detect a particular chemical, carbon monoxide.
Right.
All day long. That's all it does.
Yep.
Guess what the sour taste buds do on your tongue?
They're looking for hydrogen ions.
All day long, all night long, it's looking for hydrogen ions. And whenever one comes, it becomes super sour and you can't talk because it's like sucking a lemon or whatever. And conversely, the bitter taste buds are doing the exact same thing, except they're not detecting hydrogen ions, but hydroxide ion.
And there's actually some other things they look for as well that look for bitter things. So looking for things that contain nitrogen and some other complexes of nitrogen. And we'll talk about later why things with nitrogen tend to be basic.
Yeah, it's not just hydroxide. It's any kind of basic substance. And it's a little more complex than that. But that's kind of gives you a perspective on that.
Yep.
Anything else? We could probably talk about indicator colors.
Oh, yeah.
This turns phenolphthalein
colorless. Acids make phenolphthalein colorless. And the reason we throw phenolphthalein in there is that you use it all the time in acid-base titrations. And phenolphthalein becomes pink
I should use
in
the
a base.
pink
Oh, yes,
ink.
you probably
The pink ink.
Yes.
I'm a poet. A pink ink.
You know, that shows up in one of my son's books.
The pink ink.
Yeah.
Also, there's another one. We'll just continue to add this. There's a bromothiamyl blue, BTB.
BTB.
And for an acid, of course, it is
Is
yellow.
it blue? Oh, it is yellow. Okay, I was getting mixed up which way it goes.
And for a base, it's
blue.
Blue. That's how it's base blue.
Base,
That's how I've always remembered that.
That's good.
Yeah, well, I'm pretty good about those things.
I like
that. Is there anything else we should talk about?
Nothing comes to mind.
Oh, yeah, pH.
Think of it. Oh, yeah, pH. Duh.
And in acids, of course, the pH
pH is less than 7.
It's less than 7, and the pH, of course,
greater than 7 for bases.
7. Yeah. All right. And 7, of course, it's neutral. Okay, you probably know this. Okay, this is review. All right. Now, I don't know if you know this, but there are 3 ways that we can define acids.
Yep.
There's the Arrhenius method. Old dead white guy, Arrhenius.
Yep.
Okay.
And his acids were hydrogen ion donors. And we've talked about
No, that's Bronsted-Lowry, Mr. Sams.
What?
Yeah, that's...
For acids?
That's Bronsted-Lowry.
Aren't they both?
No.
I thought they had the same acid definition.
No, they don't.
They don't?
No, Arrhenius basically
Well, correct me.
hydrogen ion producers.
What did I say?
You said hydrogen donors.
Oh, I see.
And
okay.
bases make hydroxides. This is what we just talked about, essentially.
Yeah.
So if you have hydrogen ions, it's an acid. If it's a hydroxide, it's a base. That is called the Arrhenius definitions
Right.
of acid bases. Now we move to the second dude, actually 2 dudes, Bronsted and Lowry. They said that acids are
Hydrogen ion.
actually proton
Or hydrogen ion. Yeah.
donors. Now, what do you mean? What do you say? I said proton, you said hydrogen ion. What's up with
well,
that?
it's the same thing. A hydrogen ion. Well, hydrogen atom is 1 proton and 1 electron. But a hydrogen ion, if it loses the electron, what do you have left? You just have a proton.
So you see, if you lose an electron, ladies and gentlemen, from a hydrogen atom, it becomes a hydrogen ion, or H positive.
Also called a proton.
But
because
all that's left is actually the proton, so a proton and a hydrogen ion are the same thing. In fact, there's like a cool video that's called the Proton in Action or something like that. It's really cool science video. I'm sure you thought that sounded cool.
I
to
did.
You.
Protons in action.
Yeah, so protons in action, or the something proton. I've lost it now. All right, they donate protons, or you might think hydrogen ion donor. Okay, bases are
Hydrogen ion or proton acceptors.
So if I give you a hydrogen ion, you become a
I become a base because I'm accepting it.
Okay. All right, and I donated it to you. That
So
would
you're the
make
acid.
me an acid. Now let's do some examples under this one particularly. Yeah, we probably should. I guess we do it later here, don't we?
Yeah.
Never mind. We'll go back to the Lewis thing, I think.
Yep.
All
Lewis acids and Lewis bases.
There's a guy by the name of Lewis. He's the same guy, by the way, who did the Lewis dot structures, if you recall,
Yep.
from last year, which we will get back into later on in the year. But we don't need to worry about that at this time. They are a little bit different. They are
Yeah, the Lewis acid is an electron pair acceptor. And then the base is the electron pair donor.
What does that mean?
Well, should we show them an example?
I think we probably should.
Yeah, let's do an example.
Now, because Mr. Lewis was like the electron dot guy,
Yep.
we draw dot structures. So if I take ammonia, which is NH3, which is a base, which
Yep.
we'll discover in a minute, and I react it with, say, BF3,
Boron trifluoride. And if you're looking at this going, why does boron only have 6 things coming off of it? It's because it can be electron deficient. It's okay like that.
he's actually violating what you would call the octet rule.
Yep.
And he does not have enough electrons. He is unhappy, if you will. And if we then react these two together, you see the ammonia right here can donate his 2 electrons to the boron. I have usually called these the gluon reactions. They just glue together.
Yeah.
And you get BF3 But you see, boron wanted those 2 electrons, so they then live between them, and the nitrogen...
they share them with a covalent bond.
They share it in a covalent bond, and now we've made whatever this is called. It's complex.
Big giant.
But that makes sense. He donated the electrons. He becomes the electron pair donor, which makes him a base, and he is the electron pair acceptor that makes him the acid.
That's right.
Actually, I should go back to one more thing on Bronsted-Lowry. How do you remember that Bronsted-Lowry base acceptor acid donor? How do you memorize that?
I don't know anything clever. I just know them. Would you have something clever to show us, Mr.
What
Bergman?
does a sheep say, Mr.
Sheep says, bah.
Very close.
My 1-year-old babies know that.
It's a sheep says bad.
Bad. Oh, okay.
B-A-A-D. Maybe it's a goat. I don't know.
Because the sheep say bah and the goats are bad.
So,
I don't
base acceptor acid donor.
I like it.
Is that pretty bad?
That's pretty bad.
Yeah, but
not quite as bad as this poem I'm going to read you next.
Oh, you have another poem?
Yeah, this is my zinc limerick.
The zinc limerick. I used to have a teacher friend of mine who's a chemistry teacher. You know what his name was?
Zinc?
Mr. Zinc.
Oh, you got to be kidding me.
True story.
There's a teacher in my high school. His name was Mr. Doctor.
Mr. Doctor.
That was kind of weird. Okay, here's the zinc limerick. There once was a metal named Zinc who got himself into a stink. Into acid he fell and reacted a spell, got dissolved, and then poured down the sink.
Oh, zinc.
It fits.
It's like pink.
It is. Pink ink sink.
Pink ink sink.
Yeah, I wrote that actually, by the way.
All right.
Zinc limerick. I didn't write Little Susie, but I
At
wrote
one point, I
Zinc
used to be a
limericks.
dink.
A what?
A dink.
Oh, dual income, no kids?
Yeah,
those are the days.
Okay.
We could go out to dinner and actually go on dates and stuff.
Yeah,
that doesn't happen much anymore.
Okay, all right, okay. What is up with here now?
All right.
Okay,
these are our definitions.
These are just a reminder of the definitions, and it's a good little chart that I made.
Yes, it is.
Okay, conjugate acid-base concept. We need to learn this. We're just going to do an example here. What if I have an acid, let's say acetic acid? I've given away that's an acid. And it reacts with water. And we've learned in our equilibrium unit just before this that there are a lot of chemicals do this equilibrium thing.
Mm-hmm.
This then turns into, I want you to kind of watch this, the reaction is going to use this hydrogen is going to connect with the water right here, and it's going to make the ion H3O positive.
That's called a hydronium ion, if you remember.
Plus acetate. You know what, we should talk about something else so before we do that. I want to jump back for just a second, back to our definitions.
Oh, yeah.
I think that one thing that we should say about, and you should just add this back in your notes, if I can find the right slide right here, is that technically we say they're hydrogen ion producers and hydroxide ion producers or whatever, but technically what's going on with the hydrogen ion is it's actually the hydronium ion. There is actually no such thing as a hydrogen ion all by itself. What's actually true is that when the hydrogen ion comes into contact with water, it turns into hydronium ions.
Yeah.
And that's actually what makes the acid the acid. That's exactly what your tongue is tasting. But chemists are essentially lazy. And it reacts exactly the same way to talk about the hydrogen ion as opposed to the hydronium. So it works exactly the same way. But in this instance that we're working on right now, we do want to look at the hydronium ion.
Yeah.
All right? So that's just interesting. Now, primarily we're going to look at the Bronsted-Lowry definition, the proton donor, a hydrogen ion donor, etc. So in this case, the acid right here, the acetic acid is giving away, you can see by the purple line there, he is giving away his hydrogen to the water, so that makes him an acid.
And since the water's accepting it, the hydrogen ion acceptor would then be the base.
So this is an instance where water is actually not considered neutral, but it will be acting as a base.
And it can also act as an acid.
But you see, since the hydrogen ion was given to the water is now called the what?
And when it became the hydronium ion, it becomes the conjugate acid.
Did I spell that right? Conjugate. G-A-T-E. Sorry about that. And then the one who did not receive the hydrogen called
the conjugate base.
The conjugate base.
Yeah. Basically, you just look for which ones are kind of related. The base becomes the conjugate acid. The acid becomes the conjugate base.
Yeah, so these are like a pair. This right here and this are a pair. And then I'll change colors here. So this is one pair, and the other pair is the water and the hydronium, if you will. So the base and the conjugate acid and the acid and its conjugate base, they're like partners. You'll see it in a little bit later.
Yeah, we call them conjugate acid-base pairs.
Another example of one that a lot of people don't think about is ammonia. NH3 can react with water. Now I'm going to write water a little bit differently, you'll see. And these are both equilibrium reactions because they're weak acids and weak bases. And these are going to make, what's going to happen here is the water, the hydrogen, the first hydrogen in the water, is going to connect with the ammonia and make ammonium. And then that leaves the hydroxide. So we can now label who's the acid, the base, and the conjugate acid.
Well,
base,
water
etc.
gave up its hydrogen, so that's going to be our acid. And last time it worked as a base, and this time it's working as an acid. So water can be both. It has a special name. Actually, it's called amphoteric.
Yeah, well, let's say that for a second. Let's finish this, and
Sure.
I agree we should talk about that. The acid then gives it to the ammonia, so that makes this the base. That makes this the
Conjugate acid.
conjugate acid. And this is the conjugate base. You'll be asked in your homework to identify the conjugate acids and conjugate bases.
Another way to look at the conjugate thing is if you reverse the reaction, which one would be the acid?
Yeah.
So if you reverse the reaction, the ammonium there would be the acid. So that's
he would give his hydrogen away,
right.
So he could become ammonia.
So that helps you detect which one's the conjugate.
Now, Mr. Sams just mentioned a little bit of a big word here. Let's write it out. Amphoteric or amphoterism. An amphoteric substance is a substance that can either be an acid or a base. So as you see in this slide, water is actually acting as an acid. And in the previous slide, the water acted as a base. So water is said to be a
amphoteric substance.
Amphoteric substance. So there you go.
Alrighty.
All right. Now, that also leads us to this concept of the acid dissociation constant, which means that some acids are strong and some acids are weak, which we should probably talk about. Actually, we do right here. We can. Is this out of order?
I think since it's equilibrium.
Yeah, we can do it. We've already talked about equilibrium.
Yeah.
So let's take that reaction that we had just a minute ago, HC2H3O2. This is acetic acid. We could just say that it dissociates into hydrogens plus acetates.
Right. Now, all he's done here is he's basically removed water from the equation. He removed the water molecule on the left, and he removed the water ness from the hydronium ion from the right.
Let's write it both ways,
let's,
maybe, and then talk about the difference.
Yeah. Now, if you remember in your equilibrium chapter, the last chapter, chapter 13, we do not write solids or liquids in our equilibrium expression. So by removing liquid water from this from the equation, it makes the equilibrium easier to write because we don't have to ignore anything. We just get rid of it ahead of time.
So I'm putting all the states of matter in all these.
Yeah.
So we have aqueous here, aqueous, 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 liquid, aqueous, aqueous. So now we can find the K, equilibrium constant. Now we've been learning a lot about Ks, and you've gotten good with these. This is called the Ka for acid, and it is going to be, just like it did before, the products over the reactants, which in this case would be the hydrogen, or you could write hydronium, it would make no difference, times the acetate divided by the acetic acid. Now, a lot of students sometimes struggle a little bit with the concept that this is aqueous, but it's not dissociated.
Yeah.
That's a little bit weird. Why is that, Mr. Sam?
Well, just like a sugar molecule, if you dissolve it in water, it's aqueous, but nothing is dissociated.
Yeah.
And this is what we call a weak acid, and weak acids do not dissociate very well.
So it does dissociate, but only partially.
Right.
So only some of them have broken apart.
Right.
Broken
So
apart.
it dissolves like a covalent compound, but it dissociates a little bit like an ionic one.
And then there are tables. The values of the Kas tend to be very small. So you look at the table that's in your handout there.
Yeah. These are all going to be less than 1.
Notice all these numbers are less than 1. And so you have very small numbers. This is the biggest one that I know of that's considered a weak acid, and down to phenol, and you can see different atoms. In fact, you can even see here the ammonium atom, or ion, pardon me. The ammonium ion is a weak acid.
Very weakly acidic.
It's very weakly acidic, which we just kind of talked about just a little bit ago as a Bronsted-Lowry acid.
Yep.
Okay, how do we know about acids and bases in terms of their strength? Well, strong acids, it's easy to know about. What is a strong acid?
Strong acids are ones that fully dissociate when you dissolve them in water. And we say 100%, it's more like 99.999 something, because there's no such thing as really as 100% dissociation. But we say, for all intents and purposes, they 100% dissociate.
And the word dissociate really means to break apart into ions. Now, the word dissociate actually is used out in the regular world. What does the word dissociation mean, excluding the concept of acids and bases?
It's like when you break up something, like
you
dissolve a company or...
Yeah, you can dissociate a company, you can dissociate a relationship with somebody. Let's say that you're going out with a girl and or a boy, and one of you people say, "That's it, we're done, let's dissociate."
So it's kind of the opposite of an association.
Yeah, it's the opposite of association. All right. And then what's a weak acid?
Weak acids are ones that do not completely dissociate. Typically, 1% of it'll, ballpark number, will dissociate.
So yeah, this is like 1% breakup.
Yeah, it's like 99% of it would still be stuck together, and then 1% has split
Actually,
up.
let's say one more thing here about
Sure.
the strong acids. That the reason that the strong acids completely dissociate is because they have weak bonds
Yes.
that hold them together. And conversely, if a
weak acid has strong
weak
bonds.
acid would have strong bonds. I know that sounds kind of weird, but that's the truth because, yeah, it is.
Yep.
Let me do a little diagram for you to help you give a perspective. If I have a strong acid, so I would like you to copy this little thing down in your notes, in the note section. If I have a strong acid, and this is the acid, let's just call the acid HA, and this will be before you drop it into water. You do need water to draw the acids.
Yeah.
And then after, what are you going to find?
You're not going to have any HA, you're going to have H pluses.
HA is this much, but H positive and A negative is going to be the same
as
amount.
what you started with. Right. So if you had 1 mole of your strong acid, when you put it in the water, you're going to have 1 mole of hydrogen ions and 1 mole of the anion.
Conversely, if I were to do a weak acid, the graph would actually look quite a bit different. Before, this would be the weak acid HA. This is the before picture. Actually, I would prefer to flip that. Oh well. After, what's going to happen is you're going to have,
Just about as much as you started with of HA.
and then of the
A
H's,
little bit of H.
I might have drawn even too tall, frankly.
Yep, and a little bit of A minus.
You see, this is what it looks like. So you have start, yeah. So that's kind of a good pictorial way to look at that. Now, how do you know if you have an acid that's strong or weak? This is super easy because there are only a very few strong acids.
Yeah.
There are
The HCl.
hydrochloric acid,
Yep. HNO3.
nitric acid,
H2SO4.
sulfuric. That's the Susie one. Yeah.
Yeah,
Okay.
little Susie drank it. Let's see. HClO3. Chloric acid.
How about
Or
HClO4?
F4, sorry.
Perchloric acid.
My mistake. HI. Happy acid. Hi.
Hi. Hydroiodic acid.
Yep. HBr.
Hydrobromic acid.
And those are usually the 6.
Yeah,
I have them memorized.
that's the
Yeah,
big
that's
6.
the list. There are others, but nothing you'll ever encounter in this class.
Bases are easy. We could quickly go through the strong bases, also completely dissociate.
Yep. By the way, if you learn the 6 strong acids, everything else is weak.
Yeah.
For ones you'll encounter. Alright, so same thing with bases. Strong ones completely dissociate, weak ones only partially.
Super easy. Just
Exact
get that
same
now.
thing.
Now, there are something we should talk about in terms of the bases are a bit odd because
Mm-hmm.
most bases that are weak are actually let's just chat about something first. The strong bases would be like sodium hydroxide. It completely dissociates into sodiums plus hydroxides. And
Yep.
most people think that the bases are going to all be hydroxides, something bonded to hydroxide. And those are. But most bases are not hydroxides.
Right.
They are what we call amines.
And those are things with nitrogen.
They have nitrogen. So we did an example a bit ago, and that was ammonia, NH3. So NH3 reacts with water. The rule isn't that it contains hydroxides, but that it produces hydroxides. These are all weak bases, it turns out. That makes ammonium plus hydroxide. Hence, here's your hydroxide. So even though in ammonia there's no O's at all to make a hydroxide, you can make it by adding it to water.
Yep.
So lots of these, and you'll see some examples on the table that we'll see a little bit later.
Right.
Strong bases, frankly, there are just a few.
There's a few. Alkali metal hydroxides.
What's an alkali
essentially.
metal?
That's the group 1, like lithium, sodium, potassium, rubidium, cesium.
So if you go
All
to
of
the
those.
table number, or column number 1 on the periodic table, excluding hydrogen, of course, then you have lithium hydroxide, sodium hydroxide, etc., down to
Potassium hydroxide,
cesium
yeah.
hydroxide, potassium,
Yeah.
etc.
Common ones, lithium and potassium hydroxide are the two most common ones you'll see.
Actually, potassium too.
Yeah.
Did you say potassium?
I think I said sodium and potassium.
I thought you said lithium and
I
sodium.
might have. I don't know.
Whatever.
I need
These
some
are the
lunch.
3 big ones. Yeah, you're hungry, and so am I. Okay.
That's why I had some Laffy Taffy with malic acid.
There you go, the malic acid, man. Okay, pH and POH. All right, we've already discussed that pH 7 is neutral. If it's less than 7, it's an acid.
Yep.
If it's more than 7, it's a base.
Mr. Bergman, why is water pH of 7? And why do we call that neutral?
Well, that's pretty simple because you see water you know, water dissociates. Did you know that?
I
hope
did
you
know
knew that.
Yes.
You think his water is HOA?
It would have been foolish to hire me if I didn't know that.
Yeah, if you didn't know that, we'd had a problem. Do you know it breaks apart? One every trillion breaks apart into H's and OH's. So if you were to take a view, a download picture, all right, go into a beaker filled with water.
Put on your little scuba suit again.
And then, you know, you watched the Magic School Bus?
Oh, yeah.
Yeah, Mrs. Frizzle. Well, she
Yeah.
like took the bus, take the Magic School Bus, and you take the Magic School Bus and you shrink
nice.
yourself down. Like the yellow?
I like it.
Yeah.
Ooh,
Does that
little
look like a bus?
moving lines there in the back indicating it's traveling forward.
Now it's going to dive in the water and shrink itself way, way down. You know what you'd find? You'd find lots of,
Lots of H2Os.
and they would be like little Mickey Mouse heads,
Mm-hmm.
orientated in different directions. But you know what? Every trillionth one, you know, you'd find?
Split up.
You'd find an OH and an H.
Ah.
So every trillionth one breaks up. You say a trillionth, that isn't very many, is it?
But it's plenty.
It is quite a bit, actually. So 1 in every trillion breaks apart. And so we can actually write a K expression. Remember the Ks? We can
Yes.
say the KW
W for water.
duh, equals the hydrogens times the hydroxides. And there's a value for KW at
You know,
25
Mr. Bergman,
Celsius.
why didn't you put that over HOH?
Oh, yes, a
It says
good point.
products over reactants.
Well, because this
Ah,
is a liquid. And if
yes.
it's a liquid, you do not
Not
count it. Yes, good point.
Include liquids in equilibrium.
So that is equal to 1.0 times 10 to the negative 14th. Hence, the scale of 14, as you'll find out in a little bit later.
Oh, yes.
So this is the KW expression, and this is the value of it at 25 degrees Celsius. It's a little different temperatures. We won't worry too much about that.
Close enough.
Close enough. Okay, so that says that we can actually measure the P. P, by the way, if you didn't remember this from last year, is actually a logarithmic function.
Yes.
So the pH is the negative log of the concentration of the hydrogen. What units does the concentration have to be in?
Moles per liter.
Yeah, which is molarity
Yes.
equals moles per liter.
Yeah, and the little brackets, in case you forget, that means concentration.
And then P, so negative log of the concentration of the hydroxide atom, or ion.
Yeah.
pH plus pOH is always equal to
14.
14. 10 to the negative pOH is equal to the concentration of the hydroxide. And 10 to the negative pH is equal to the concentration of the
Hydrogen.
hydrogen.
We did that last year, and we did it earlier this
And
year.
we just wrote
so
this, but just for grins, the concentration of the hydrogen times the concentration of the hydroxide is equal to 1 times 10 to the minus
negative
14th. And you recall the scale is a scale from 0 to 14. You know, 0 to 7 is an acid, and 7 to 14 is a base, right? So the scale is actually measuring how much hydrogen ion is in the solution. If there's a lot, then if there's more hydrogen than hydroxide, it's an acid. If there's less hydrogen than hydroxide, it's a base, and it's equal to acid.
Yep.
Now here's a little chart here to kind of give you some perspective. Battery acid has a pH less than 0. Okay. Yeah, you can be less than 0. You can
Yep.
be up to -1. Household lye is way down here, and here's of course freshly distilled water 7. Milk's slightly acidic. Egg yolk 6 point some change, or 5 and some change. You can read the
Yeah.
chart here.
Read the
You're
chart.
good. Okay. Now how do we convert from one to the next?
Now, before we fill this in, guys, hit pause and try to fill this in yourself.
Yeah.
Just do some practice. Maybe watch us do the first one and then go back and do some more. But don't just sit and write down everything we put in here, because that won't help you at all.
Yeah, and we've done something like this if you were in our class last year. So essentially, when I look at this first column and I see a pH, the pOH is the first thing I want to calculate, because I can do 14 minus 2.3, and that's going to be 11 some change, 11.7. Now to do this hydrogen concentration, I will say 10 to the negative 2.3 power is how I would do that.
And that is 5.01 times 10 to the negative 3.
And I would just do 10 to the negative 11.7 on that one.
And that is, whoops, I punched the wrong button. 10 to the negative 11.7. We get
2 times 10 to the minus...
2 times 10 to the negative 12, essentially.
Now, by the way, how do you know if it's an acid or base? I always just look at the pH, not the pOH column. The pH is 2.3, so that makes this an acid.
Yep.
Now, this would be very simple. I would do 4.5 minus 14 and be 9.5. Which, by the way, I could just jump over here and say that's a base, right?
Yep.
And this would be 10 to the power of negative 9.5.
And that is 3.16 times 10 to the negative 10.
And this will be 2 point something times...
3.16 times 10 to the negative 5, interestingly enough.
Okay, now, if we have this number first, the hydrogen ion, then I can take the log of this number,
Negative
negative
log.
log of that, and that will give me the pH, which would be...
4.47.
Subtract that from 14 gives me
9.53.
And then I could take 10 to the negative 9.53.
10 to the negative 9.53 is 2.95 times 10 to the negative 10.
And that would be a what?
That looks like a pH4 acid. Yep.
Yeah, look in the pH. I just look at the pH column for that. Okay.
Yep. Do we want to talk about sig figs and taking logs?
Oh, you know, we ought to do that. That's a good point. A very good point, actually. Whenever you take the, how many sig figs do you see if a pH is equal to 11.7?
Looks like 3 sig figs.
Yeah, but that'd be wrong, Mr. Z.
Yeah, I know it is.
I know you do. But here, you see, the thing with pH, because really, if you think about it, the 11 right here, if you're thinking mathematically, the 11 is actually showing the power of 10. And the 7 is the actual value. So sig figs and pHs, this is actually considered to only have one sig fig. And that sig fig is the 7. You see, the sig figs, you only count numbers past the decimal.
Right.
So if I've got a pH of 6.27,
that looks like
that's got 2 sig figs. And if I have 12.27, that's also considered 2 sig figs because you only count the decimals past.
Right. So if we want, let's say we want to calculate the concentration from 6.27, I go 10 to the negative 6.27.
And you're going to get 5.
Since that number had 2 significant figures, my answer should have 2 significant figures, and that would be 5.4 times 10 to the negative 7, if you put that in your calculator. Okay?
All right. So have we done this appropriately?
I think we've probably beat that into the ground enough. We have not. Sorry. Actually, our sig figs are wrong in here. That's why
what I was
just
thinking.
noticed
this
it and thought
number
I'd bring it
here
up.
is wrong and wrong because we only have one sig fig in this answer. We have only one sig fig here, so I should just say 3. And this will be
3.
3.
And then those were 2, so those do have 2. Those are correct.
Yeah, 2 and 2, so that's correct. We should jump down and maybe do this one right here, this last one.
This one...
I don't even need a calculator.
No, we can do this one in our heads.
I think this is 7.
This is magic.
7, and of course this makes this
Neutral.
neutral. Now, how do we do this? Well, 10 to the negative 7th is 10 to the negative 7th.
Right.
So it's 1 times 10 to the minus 7th.
Yeah, if it's just a single number with no decimals, you put 1 times 10 to the negative, and whatever number it is there, that's the number you put for the exponent.
I don't know that we need to do this one. I think you've got the idea.
I think you got it.
Okay, ladies and gentlemen, you got any more limericks or?
Oh boy, yeah, I do. I have a haiku about oxygen.
Haiku?
Yes.
What's a haiku?
5 syllables, 7 syllables, 5 syllables. All right, here we go. This is my oxygen haiku. I will breathe you in. Cellular respiration. Out goes CO2.
That was it?
It's a haiku. 5-syllable line, 7-syllable line, 5-syllable
So the
line.
O2 goes in and the
beautiful.
CO2 goes out.
Yeah.
But I must have missed the art.
Cellular respiration.
Cellular respiration. Say it
Yeah,
again?
I will breathe you in. 5 syllables. Cellular respiration. That's my 7-syllable. You gonna hold your breath? Okay. Out goes CO2. You're a swimmer. You can hold your breath.
I
Bye,
just
guys.
exhale. All right, bye-bye.
See you in class.